Hello there, Mr. Sutton here, bringing you this AB Calculus 3-2 lesson on differentiability, the first of two parts on this topic. In this one, we will be trying to understand differentiability and find its intervals. As our starting point, pause the video, take a look at this graph, and see if you can estimate dy dx, the slope, at each of the following x values. Okay, let's see what we came up with here. So at -3 over here, we're flattening out, so it looks like we're approaching 0. Whether or not we actually get there, that's pretty close to what the slope is over there. At -2, at this vertical asymptote, not really sure what the slope is. I mean, it looks like we're getting kind of infinitely steep on either side, so we'll put a question mark there. At -1, at this little pointy spot here, also not really sure what that slope is, because from different directions we've got, we're infinitely going up, infinitely going down, so not sure about that. At 0, this is infinitely steep looking here, not really sure about that slope either. Man, we're striking out a lot here. At 1, we're turning around, so at this instant spot right here, we could say the slope is 0. We're pretty close to it. Over here at 2, well, it looks pretty steep, but beyond that, I mean, we have this discontinuity. I'm not really sure what we're supposed to do with a slope at a discontinuity. At 3, to get to 3, we're going down 2 and over 1. So we could say the slope here is -2. So a whole bunch of question marks so far. Now that we've talked a bit about what derivatives are at certain points, let's talk about what it really means to be differentiable at a point. A differentiable point is basically somewhere where the derivative exists. This means it meets two criteria. First off, the point must be continuous. So that means that the limit must exist at that point, the function value must exist, and those two things have to actually equal each other. The other condition, and this one's a little bit new, is that the slope at the point has to approach the same finite value from both sides, which is to say the limit as x approaches c from the left of f prime, and as we approach that same number from the right of f prime, those have to match up. In our next lesson, we will officially test for differentiability. Right now, we're just getting a feel for it, and a good way to do that is to look at places where we do not have differentiability. One of these cases is discontinuities. Any discontinuity, whether it's an asymptote, a hole, a jump, or an undefined area, is not going to be differentiable, because remember, to be differentiable, you have to at least be continuous. You can't talk about whether something has a slope or not if the function doesn't even meet up at a certain spot. So something that's differentiable is always going to be continuous. In fact, one way of them being kind of sneaky and showing you that something's continuous is for them to tell you that it's differentiable, and you have to know that that also means it's continuous. Now, the reverse is not true. Just because something's continuous does not mean it's differentiable, and we'll see a few cases now where that's the case. One of these continuous but non-differentiable cases is a cusp or corner. These both refer to places where the graph is continuous, but the slope changes abruptly. In other words, we have sharp edges. A good example of this is the absolute value function. The absolute value function, we start off with a slope from the left that's -1, at least the parent function here, and as you come from the right, the slope is +1. So we have an abrupt change from negative to positive slope right here at this point. Another example is this x to the 2/3 function. It's kind of a pretty looking function. I call it the bird function here. It looks kind of like a bird. As we come from the left side, we're getting infinitely steep on the slope. It doesn't quite look like that at this level of zooming, but if you zoomed in, you would see that it just keeps getting steeper and steeper. So we have negative infinity coming from the left. Coming from the right, it's actually infinitely steep as you get closer and closer. So again, abrupt change in slope. Now, corners and cusps are technically different things. Corners have constant slopes, and cusps have infinite slopes. So this absolute value counts as a corner, and this function here is a cusp. But often the two will be used interchangeably. The other type of non-differentiable but continuous spot on a graph is a vertical tangent. This is where you have continuity, but your instantaneous slope is perfectly vertical, approaching the same infinity. So the cube root function is a good example of this. As you're approaching 0 from the left and from the right, you're approaching infinity for your slope from both directions. So it's not an abrupt change in direction. However, it's not a constant slope, so it does not count as being differentiable. Now, it's also worth noting that just because you have a vertical tangent does not mean you fail the vertical line test. This vertical tangent line occurs at a single point. It is an instantaneous slope. It's not like average slope where you would need 2 points on the same vertical line to get it. So we're going to do a couple examples now where we find intervals of differentiability, and they're going to want us to explain our answer, by which they mean identify the non-differentiable spots on the graph. Now pause the video and take a sec to see how many you can identify on this graph over here. Alright, let's see if you got all of them. Now one that a lot of people miss, and we're going to go from left to right here. If you look at the left, there's nothing on the left. This graph has endpoints. That means it has undefined areas, which count as discontinuities, from negative infinity to negative 2, and from 3 to positive infinity. So if your graph doesn't exist somewhere, it is not differentiable where it doesn't exist. Now moving on to the graph proper, as we go here, we see we have a corner at negative 1. Moving on, we have a discontinuity, a jump, at 0. We have at 2 a hole, a removable discontinuity, and it looks like that's it. So now to get the intervals of differentiability, we're just going to exclude these non-differentiable spots from our answer. So obviously we can't have anything from negative infinity to negative 2. Our answer's got to start at negative 2. So from negative 2 to negative 1 is one interval of differentiability, but then we have to leave out negative 1. And from negative 1 to 0 is the next one. Then from 0 to 2, and from 2 to 3. And so we come full circle. This is the graph that we saw in the warm-up at the beginning. Pause the video, see if you can identify the non-differentiable spots, and then find the intervals of differentiability. All right, let's see if we're on the same page. Now this goes forever to the left and to the right, so there aren't any undefined areas. Moving from left to right, we have a vertical asymptote discontinuity at negative 2, infinite discontinuity. As we keep going here at negative 1, this is a cusp. As you go to 0, this counts as a vertical tangent. And over here, let's see, we have a removable discontinuity at 2. And it looks like that's it. So from negative infinity to negative 2 is one interval. Then from negative 2 to negative 1. From negative 1 to 0. And we make it all the way from 0 to 2 before we hit another problem. And then from 2 to positive infinity is our last interval. To wrap this one up, we're going to do a little true-false, talking about the continuity of the derivative itself. So first one, true or false, if f prime of x is continuous at x equals a, that means f of x must be differentiable at x equals a. All right, this ends up being true. If f prime is continuous, that means that f prime of a actually exists, which is kind of the definition of differentiability. Now let's do another one, true or false. We're just going to switch these statements here. If f of x is differentiable at x equals a, that means f prime of x must be continuous. This ends up being false. Differentiable means that f prime of a exists. It also means that the limit of f prime exists because you're approaching the same limit from the left and the right. However, these two things existing doesn't actually mean they match up, which is what we need for continuity. F prime of a and limit of f prime could be different. You could have a removable discontinuity in the derivative, and it would still count as being differentiable. So that's it for this one. Until next time, Mr. Sutton signing off.